current slide. And let's hit a couple of announcements. Well, it doesn't go from current slide. Let's try it again. There we go. Okay. I think you've heard this one a few times before. First mini-term is over, and they were late getting it out there, but you can do your student course evaluations now. So if you know of someone, even if you didn't take one yourself, that was in a first mini-term course, please encourage them to get these done. Even though they're late putting them out there, we still would love to get the data. Okay, so that's that. And I think I've mentioned before that means also there's midterm. We passed it, okay? And at some point, they'll probably be asking for midterm progress reports. And even though in the other class I've gotten some work from you, I haven't gotten anything from this class. So I need something this week if possible. First test, you now have the second test too, right? Didn't I give that out last week? Maybe not, I don't remember. I know, but before last week, I thought I ran it off, and maybe not. Let's see where it is. Okay, I guess I will be finishing it today. Perhaps. Okay. No, I don't have it run off. I thought I did. But the first test and the research paper have both been assigned, so I'd like to have at least one score sometime next week. So if possible, please get that to me. I don't know. Just to give you a sort of an idea, last week they wanted summer schedule in by Friday. They had to have it in by Friday. And they had to have fall schedule, which is the biggest schedule of the year, in by today. And it's just nuts. And I got summers in, and then I have a lot of falls done, but not all of it. Because for the last, I think, 3 years, they've changed the entire developmental way we do developmental scheduling every year, okay? And that means doing them all from scratch. I can't just use what was there before. I have to do almost totally new things. So it's not been fun. Now, and I think I also told, did I tell y'all in class yesterday about the results of my doctor visits? Huh? Oh, okay. I found out last Tuesday when I was at the doctor, and I was too late getting back to have class. Part of the reason for that is, well, my blood work was late. In fact, I still didn't get a copy of it by the time I left. But the nurse was concerned when she first looked at it on the computer. It wasn't ready to be printed. The preliminary stuff, she said I was very anemic. And when the doctor came in, he started asking about if I changed my diet, because I was very anemic. Now, I've always been slightly anemic whenever I've been taking the treatments. They never are targeting enough just to hit the white cells. They wipe out some red cells and platelets, always. So most of the time, slightly anemic. But now it's not slightly, it's very. So they put me on B12, just over-the-counter type stuff, vitamin B12, which is supposed to help boost that a little bit. He said it didn't look like it was an iron deficiency because the shape or size of the cells were good. It's just that I didn't. And what he feared, I think probably what's happened, the proteins or the whatever it is in the treatment that attacks the white cells, they must have wiped out most of the white cells and started attacking red cells too. They weren't supposed to, but they did. So anyway, that was one bit of bad news. But it did explain why I've been so tired. Okay, I thought it was just because I was 69 years old. I've never been 69 before, so I thought This comes with age, but I found out now it's because I am very anemic. Well, like I said, they didn't have, well, and then he wanted me to go back and they took like 3, 4, 5 something tubes of blood like they always do before the thing. That's how he saw what the counts were. And he sent me back to get 5 more tubes done so he could see what was going on with the red cells. And so far I haven't heard anything back, which I take to be good news, that there must not be anything real badly wrong with them, you know, so, but I don't know that for sure. I'm just assuming. But then, so I went by, I had a dermatology appointment on Friday, so I went by there after the dermatology appointment to see if they had copies of my blood. I like to, and my wife especially likes to have my blood, results of the lab work. And the nurse said, oh yeah, here they are. Like that. She said, oh, your immune system's also really low too. So it's the immunoglobulins, IgG, IgM, and one other IG something another. They were all low. So this thing was really, the treatment did a great job on the white cells, but it also sort of bashed around everything else too. So I don't know. He's going to see me in 3 months and decide what to do next, see if the counts bounce back, which counts bounce back. So anyway, that's that. Sorry, too much of that. So, oh, and well, the thing about the low, the immune system problems, now with coronavirus coming around, if it starts happening here, which probably is more when it starts happening than if, then the odds are my wife's going to pull me out and say, nope, you can't go to campus anymore. And maybe the doctor will say the same thing. I don't know. So we'll just have to play that by ear. The things are out there. All the recordings are there. So we can continue, and I can Skype, FaceTime, or whatever you need to do to try to wrap up the course and email you the test or whatever. All right, but anyway, hopefully we won't have that issue to face. Now, did you all do anything beyond what we had done in class, or are we starting from there? Okay. So, according to what I have, we're in Chapter 2, Matrices, 2.4 Elementary Matrices, Example 6 on page 80. Is that about where you had us being? The last thing we would have done was example 5, LU factorizations, where they just gave us 2 matrices and said show that they are LU factorization.
Oh, yeah.
Huh? Okay. So example 6, top of page 80. Find an L. This time they're not giving it to you. You have to find it yourself, the LU factorization of this matrix A. Let me get my pen set up. Okay, here's matrix A, a good old 3 by 3. 1, negative 3, 0, 0, 1, 3, and 2, negative 10, 2. Now, I just want your idea. Okay. First, what is an LU factorization? What does the L stand for in LU? Exactly, lower triangular matrix. Now, describe for me what a lower triangular matrix is. When what? Zeros in the top right corner? Yes, you got it. Basically, okay, number 1. You can only do this with square matrices. Only, okay? Now, so it has to be a square matrix. We got one. What you do is find the main diagonal. Right there it is. Okay? And the lower triangular matrix is going to be one where everything above that main diagonal is a 0. And we got one of the three things up there. It's already a 0. So that's sort of bonus there. Okay. Now, what does then the U stand for? That's the upper triangular matrix, which is? Okay. Everything below the main diagonal is a 0. And we got one out of the 3 zeros there as well. Which of these do you think is easier to produce? An upper or a lower? Lower, because that's how we go about doing Gauss elimination, right? Basically, that gave us a lower triangular matrix, right? Upper triangular matrix. Did you say lower? Or did you say upper? Okay. No, actually, the upper is the one we want to do. I'm sorry. You threw me off. Because we want our Gaussian elimination, row reduction, make zeros down here, right? So that gives us an upper triangular matrix. So basically we start just like we usually do by making this a upper triangular matrix. Now, what would be your first step for doing so?
2 times row 1 plus 2 times row 1 minus row 3.
Okay, or minus 2 times row 1 plus row 3. Okay, either one of those will work. Actually, if you want to know my druthers, which I doubt if you do, but I'm going to tell you anyway, is I don't like that third row. Why not? Yeah, why don't you divide by 2? So I'm going to make this a 1 minus 5, 1. And that's going to make it even easier. Okay? I just divided everything in row 3 by 2. In fact, now that I think about it, why don't I divide by negative 2 and make that a minus 1, positive 5, minus 1. What's the advantage of doing that? Plus row 3. Okay. So, and sorry about this. Okay. We're doing it slightly differently from the book. So let me go back and write my matrix. Just to show you there's more than one way to skin cats if you don't like cats. Okay. That was a 2 minus 10, 2. Okay. Now the only advantage of doing the way you said first is it's one fewer step. So let's go with the one fewer step. I could just wipe out a row and that would have been fine, but you see what we need to do is track what we're doing with elementary matrices. Okay? So therefore, let's write the identity matrix, the I3 over here, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. You don't have to do this, but I just find it easier to refer to that. And what you said before, or between us we got it out, minus 2 times row 1 plus row 3 is the new row 3. Okay? So our first step here will produce what? 1, negative 3, 0, that doesn't change. 0, 1, 3, that doesn't change. But what will be the new row 3? 0. Negative 4. 2. Okay? Now, your E1 which is the first elementary matrix that does the same thing we just did there, would be you leave these two rows alone, 1, 0, 0, 0, 1, 0, and what's your new third row? Negative 2, 0, 1. Got it. Okay. Next. And again, we're going to go with what's easy, not, well, what's fewest steps, not what's easiest. Okay. What would be your next? Yeah. 4 row 2 plus row 3 is now the new row 3. And what would that be now? 1, negative 3, 0 stays the same. 0, 1, 3 stays the same. What's the new third row? 0, 0, 14. Okay, that is an upper triangular matrix. Okay, we need to do the same thing for your E2 here. And what would that be? 1, 0, 0, 0, 1, 0, those stay the same. Now you're not doing it to E1, you do it to the I matrix up here, I3. Okay? 0, 4, 1. Perfect. Okay. Now, this is your U for this problem, upper triangular matrix. Okay? Now, what we were doing over here with the E's was in effect saying that you started with matrix A, you multiplied it by E1 on the left, and then you multiplied it by E2 on the left, because these were the identity matrices that were doing the same things as our row reduction here, right? And that gave us our U, okay? Upper triangular matrix. Now, if we take that expression right there, E1 times E2 times A is equal to U. And then by judiciously multiplying this by E2 inverse times E2 times E1 times A, that would give us E2 inverse times U, right? Right? Okay. Now, what does this give you? The what? Absolutely, that gives you I3. Okay? And you can just sort of ignore that if you wanted to. And then what we would do with that, since that's just identity matrix, we won't even write it down, multiply that result by E1 inverse times E1 times A, and that would be E1 inverse times E2 inverse times U, right? There is a minus in front of that 1 that looks like it's part of the E, but it's not.
Why would that not be A?
What's that?
Why would that not be A?
What?
This
will be A.
Oh,
Yeah. E1 inverse times A, but I just showed you multiply this by E1 inverse on the left, multiply this by E1 inverse on the left. I just showed you from this, you got to this. And you're absolutely right. You just jumped a step on me, and that was that A is equal to E1 inverse times E2 inverse times U. Well, guess what? If A is factorable by AU factorization, then this thing better, right here, had better be L. And if it does turn out being a lower triangular matrix, then we've got our answer right there. We've done the LU factorization, right? So let's see. So that's our game plan. I don't have enough room, so I'm going to erase part of this. Because now you've proven to yourself this is true, right? Okay, so I'm going to put the bottom line here up top, okay? Because I don't like it on the bottom, okay? So let's do that. Let's do A is equal to E1 inverse times E2 inverse times U. That's what we're getting at. And if these two together form a lower triangular matrix, you've just done the reduction. So I'm going to erase it down here. The reason I'm going to erase it here, I wanted to write in this place what E1 inverse is. And you tell me what it is. Hint, these two lines are the same. I know that was a surprise to you, right? Okay. Now, the question is, what operation do you do to this to make that back into the identity matrix? Because that would be the inverse of this, right? You don't do anything that's top two rows, but what do you do here? Two times that plus this will give you the identity matrix, right? So that means 2 times that. And what would that be? 2, 0, 1, right? 2 times row 1 times added to row 3, right? And if you go back to page 77, you'll see that when you did the row operation we just did, multiplying one row, in fact, it's identically the same thing. Their E2 on page 77 is exactly our E2 here, so their E2 inverse is exactly our E2 inverse. So that's good. What would be our E2 inverse here? I don't know what this thing's doing. If I hit X here, will this everything go away? I hope not. Yuck! It did go away. So I'll get them back. Except everything I just had is now erased. Yuck! I don't know why this just... I'll tell you what else is going on. I think I probably told you before. After a little while in this room, when I'm plugged in here and operating, my power starts diminishing and flickering. I've never had this happen at home. I've never had it happen, I don't think, on the Birmingham campus on Fridays. I don't think I've ever had it in my office. I keep telling them there's something wrong with this plug. Now, it may not be the plug. It may be I just leave it on too long. Maybe my converter is getting too hot. Maybe this is getting too... I don't know what it is, but it's not... I don't have it happening everywhere. And it's just so frustrating. And here we go. Okay. Let's see. just to recap what we had, I've got to get my pen back. Okay. We had A was this matrix here, 1, minus 3, 0, 0, 1, 3, and 2, negative 10, 2. Okay. The upper triangular matrix we got from this was 1, negative 3, 0, 0, 1, 3, 0, 0, 14. I don't know that we need that, but just in case. Okay. I don't think we need E1 anymore. We do need E1 inverse. And that was 1, 0, 0, 0, 1, 0, 2, 0, 1. We did have E2 to be 1, 0, 0, 0, 1, 0, 0, 4, 1, right? What we need is E2 inverse. And what would that be? Got it? Got it? Negative 4, 1. Excellent. Okay? Now, the other thing we had was that A was equal to E1 inverse E2 inverse U, right? So all we need to do is multiply these two together and see what we get. Now, just as an observation here, this one is, this elementary, inverse elementary matrix is what kind of matrix? Lower triangular, and this is lower triangular. So I have a real warm and fuzzy feeling that the product may be lower triangular as well. Let's see if it is. Let's multiply those two together. That's going to be blank, 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 and blank, blank, blank. Okay? First one gives us a 1. 1, 2 gives us a 0. 1, 3 gives us a 0. 2, 1 gives us a 2, 2 gives us a 2, 3 gives us a, boy, not much here, is there? And 3, 1 gives us a 2, 3, 2 gives us a 3, 2, negative 4, and 3, 3 gives us a 1. Sure enough, that is a lower triangular matrix, isn't it? And is indeed that lower triangular matrix. Ooh, yeah. If we multiply that one, 1, 0, 0, 0, 1, 0, 2, negative 4, 1, by the upper triangular matrix we had earlier, 1, negative 3, 0, 0, 1, 3, and 0, 0, 14. I wonder what we get. Be a 3 by 3. Okay. very well spaced threes, but whatever. What you get first? 1. 1, 2 gives us a, that's all. And 1, 3 gives us a 0. 2, 1 gives us a, you say 0? Is that what you said? Okay, I'm sorry, I misunderstood. And 2, 2 gives us a 1. And 2, 3 gives us a 3. 3, 1 gives us a 2. 3, 2 gives us a negative 10, and 3, 3 gives us a 2. Is indeed that A? Yes, it is. So sure enough, we have found our LU factorization of that matrix A. It would be 1, 0, 0, 0, 1, 0, 2, negative 4, 1 is a lower triangular matrix, and the upper triangular matrix 1, negative 3, 0, 0, 1, 3, and 0, 0, 14. Okay. Pretty ugly writing, but other than that, it's okay. Now, what they say here L is the product of the inverses of elementary matrices used in the row reduction. And it says, note that the multipliers in example 6 are negative 2 and 4. That's how we got to E1 and E2, but which are the negatives of the corresponding entries in the lower triangular matrix, which is, where's our lower triangular matrix? That's this one. 2 and negative 4, okay? Yeah. This is true in general. If U can be obtained from A using only the elementary row operations of adding a multiple of one row to another row below it, then the matrix L is the lower triangular matrix along with ones along the diagonal, and the negative of each multiplier is the same in the same position as that of the corresponding 0 in the U below the main diagonal. Blah, 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 blah. Okay. Once you've obtained the LU factorization of matrix A, you can then solve the system of n linear equations in n variables A, X equal B very efficiently in 2 steps. Okay, so I think I'm going to have to erase what I've got here and write this down. So here's what our problem is. We have some matrix A, by the way, it needs to be a square matrix, times some row vector X, those are your unknowns here, is equal to some known constants. Another, I'm sorry, I said row, column matrix B, column matrix X, column matrix B, okay? If you know that A is equal to LU, okay? If you already have determined that, or they gave it to you, or somehow you know that A is this thing here, then what you do here Here are your two steps. And I don't see them as intuitively obvious. Just almost have to. They make up a new column vector y and say that is your u times your row vector x. I mean your column vector x. Okay? So they give you that. Okay? So you know what your x is. You already know what your u is. That gives you your y. Then what you do is take your lower triangular matrix, multiply it by this y, which is ux, okay? And I don't know why they just don't write it ux, but they write it y, and set that equal to b. You solve this for y, okay? Now, that sounds probably easier than you would think it is, but let's see, okay? Then the second step, after you've done that, you solve ux, which is what your y was, is equal to y that you just solved for, okay? And you solve that for x. Now, there's something about this that makes me dizzy because it seems like we're running around in circles, okay? You're really not quite, because like I said, rather than writing y is equal to ux, if you just wrote L times ux rather than L times y, the only thing is you're not going to be able to solve for y then. But that gives you a, you have L times u times x is equal to b. Well, L times u is a. So that's basically restating what we already had, but having the y in there. And so you solve that for y, set it equal to u times x, okay? Solve that for x and you got it. Column matrix A, x is the solution because ax is equal to lux, which is equal to ly, which is equal to b. What they say here, the second step, solving for y, is just back substitution because the matrix U is upper triangular. The first step is similar except that it starts at the bottom of the matrix because L is lower triangular, and for that reason the first step is also called forward substitution. So a lot of blah blah blah. Let's just do one and see if it makes a little more sense than everything they said. So here's what we're going to start. And by the way, you can go to larsonlinearalgebra.com for an interactive version of this type of an example. So here's what we got. X sub 1 minus 3x sub 2 is equal to negative 5. X sub 2 plus 3x sub 3 is equal to negative 1. 2x sub 1 minus 10x sub 2 plus 2x sub 3 is equal to negative 20. Now again, if we were in any other situation, I would say look at that bottom equation and divide everything by 2. There is no reason to have more complicated numbers than you need to. But there is a reason I'm not going to say do that. And that's because if you look at the coefficient matrix here, the A times the X, what's that coefficient matrix? Example 5. Exactly the one we've already done. So we already have the LU factorization. If you did anything to it, it would change your LU factorization. And since we don't want to do that, we're going to leave it alone, much to my chagrin. Okay, so just to remind ourselves, our A here is that same matrix, 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2. Okay. Our X vector is x1, x2, x3. And our B vector is, this is new now, negative 5, negative 1, negative 20. Nothing that we've done already had anything to do with that. Okay. Now, we already know the LU factorization of this one, or we did at one time. The lower triangular matrix was 1, 0, 0, 0, 1, 0, and remind me, was it 2, negative 4, 1, or, yeah, that was it, wasn't it? 2, negative 4, 1. That was your L. Your U was 1, negative 3, 0, 0, 1, 3, and 0, 0, was it 1? Why can I not see it?
Those are 14.
Huh?
Those are you.
Oh, yeah, it's a 14. That's right, I remember. There it is. Okay, 1, negative 3, 0, 0, 1, 3, 0, 0, 14. Yeah, and that's our U, upper triangular matrix. All right. Now, okay, so I think we got all the pieces. Now let's put them into place. Okay. There it was right in the book. Okay. So they first say let y equal ux. So y is just some brand new vector we come up with and say it's u times x. Okay. Well, u is our upper triangular matrix, which is 1, negative 3, 0, 0, 1, 3, 0, 0, 14. Okay, and this is times x1, x2, x3. All right. And the interesting thing is they never write that down, do they? They just say let y be that. I wrote it down, they just say let it be ux without writing a single thing down. Okay. Then solve this system, which is ly is equal to b. Okay. And that would be the lower triangular matrix, 1, 0, 0, 0, 1, 0, 2, negative 4, 1, times b, which is negative 5, negative 1, negative 20. Wait a minute. I'm sorry. That's y. Saying this is totally wrong. I was jumping way ahead. y1, y2, y3. And this is equal to b, which is negative 5, negative 1, negative 20. Okay. Now, like they said before, this is kind of like forward substitution. Let's start at the top, and that gives you y1 is equal to y1 plus 0, 0 is equal to negative 5, right? y2 in this case is negative 1. And then the bottom line says 2y1 minus 4y2 plus y3 is equal to negative 20. You buy that? But we already know what y1 is. This is 2 times negative 5 minus 4 times negative 1 plus y3 is equal to negative 20. Have room to write somewhere. Negative 10 plus 4 plus y3 is equal to negative 20. So y3 is equal to, let's add 10 to both sides, you get negative 10. Subtract 4, you get negative 14. Right? Yay or nay? Okay, so there's your y. Negative 5, negative 1, negative 14. So I'm going to reverse the order of this and write this ux here. 1, negative 3, 0 times x1, x2, x3 is equal to y. And that would be negative 5, negative 1, negative 14. Fill in the rest of this, 0, 1, 3, and 0, 0, 14. Okay. Since I've used what I need, I'm going to erase so I have more room to write. Are you okay with that? Okay. So let's erase this part here. Hopefully it's right. I think it is. Probably should have checked it first. I think I did glance and saw that it looked like it was right. Okay. Let me glance again and make sure it is. Yeah, well, wait. Yeah, that was right. Okay, now we're doing back substitution. Start at the bottom. 14x3. Okay, if you start with the bottom row, 0 plus 14x3 is equal to minus 14. So that would make x3 equal minus 1. Yay or nay? Okay. And then going up a row, you do 0 minus 1 minus x2, okay, 0 minus, no, plus x2, goodness, I'm on the wrong line, 0 x2 plus 3 x3, which would be minus 3 is equal to minus 1, so that implies that x2 is equal to 2, right? Okay, then go up to the top row, and you get x1 minus 3 times x2, that would be a minus 6, is equal to minus 5, so this gives you x1 is equal to 1. 1, 2, negative 1. That's your x vector. And that's what you were looking for. 1, 2, negative 1. That's your solution vector for that problem we have. Now, you might ask yourself, is this easier than Gauss elimination? I don't think so, okay? But it is probably fairly programmable, and especially if you're doing the same set of equations but with different results. Say you're running a business and your equipment can produce your A vector, A matrix. You know, you have 3 machines operating at certain capacities and stuff like this. That's always the same, okay? But you want to try different outputs that you want to shoot for, then what is the input that you would have to be for that, whatever your X is. You know, man hours or supplies or whatever. You could do multiple ones of them, and once you got the basic part done, it probably does help doing that. But I'm not promising anything there. I'm just trying to make it sound reasonable. Okay. That finishes 2.4. Homework exercises here, but includes any of the odds 1 through 7. They're all at Calc Chat. Either 9 or 11, they should both be at Calc Chat. Any of the odds 13 through 17 should be at Calc Chat. 19 through 23 should be at Calc Chat. 25 and or 27 should be at Calc Chat. 29 through 35 should be at Calc Chat. 37 is a writing exercise. I don't know if they'll have anything at Calc Chat or not. If so, you might want to look at that. 39 should be at Calc Chat. 41 is a true-false. It should be at Calc Chat. It actually has 3 pieces to it. I assume each of those is a true-false. And they all should be at Calc Chat. 43 or 45 should be at Calc Chat. 47 should be at Calc Chat. 49 or 51 should be at Calc Chat. 53 should be at Calc Chat. 55, 57, and 59 are all proofs or guided proofs, and they should be at Calc Chat as well. 61, this should then be at Calc Chat also. Now, section 2.5. Markov, I don't know how you pronounce it. Markov, I don't know how you pronounce it, changed. This is something that is done, I'm trying to remember. Just take a look here. They're not in our course description, okay? So it's not something we need to do. I'm trying to think, there's one course that really does a lot and hinges a lot on Markov chains, and I do not remember which one it is. You're mechanical or what? Electrical. It doesn't sound like an electrical issue. So, but if you found out it is, you might want to look at this section and see. I think it's more industrial engineering. Now that I think about it, would be using Markov chains. Okay, some pretty interesting things. Consumer preference models. That's why it seems like that's an industrial engineering type issue. Now, they have things about steady state matrix or Markov chain. You can read on that and see what that is. Absorbing Markov chains or Markov chains. You can follow that. So basically this whole section is varying uses and predictions and things with Markov chains. I've never done it before. Not in our course description, so I'm skipping that one. You see all sorts of exercises there. If you find out it is something that would be valuable or necessary for you, by all means, look at it. 2.6, more applications of matrix operations. One is in cryptography, which is pretty interesting and fascinating, and there is a lot of good stuff out there. There was one time on public television, a show on the Bexley's house or something like that. Basically what it was the British trying to figure out ways to break the German code. And I know for a fact that in World War II they did so. And that was one way they were able to defeat the Germans. And there's a really sad story. Did you see the movie on Churchill? Can't remember the name. Darkest Hour, I believe was the name of it. It was a section of that, and I think this is historically true, where they found out the Germans were going to attack or isolate this British outpost they had here, but they discovered this by using the code they had broken. But they were planning, I think, D-Day assault, or it was planning Dunkirk 1, okay? And they needed to have that intelligence in order to pull off Dunkirk or the D-Day or whatever. And they knew if they gave it away that they had broken the code and rescued that outpost, the Germans would know they had broken the code. So they actually had to sacrifice. Germans came in and wiped them slick. And it was a heart-rending decision to let those men die or get captured or whatever. But it could have prolonged the war, or maybe even changed the outcome of the war for them to let that go. So cryptography is a fascinating field, and they use matrix operations to do so. You encode one way, decode another way, inverse matrices. It's used there as really a fairly fascinating procedure, okay? The next application here is, and I don't know how to pronounce this guy's name, Leontiev or something like that. He was an American economist, which was a surprise to me. I would have sworn this was a Russian name or some other name, but he published a model concerning input and output of an economic system. He won a Nobel Prize for his work in economics, and here's his model, the Leontiev, or however you pronounce that, input-output model. And it is, I mean, it's reasonable, doable, but it's really kind of involved. And you can really get bogged down in it pretty easily. Okay? A second one. A third one. Now, this is one not in our course description now, but if I'm not mistaken, because I was at a meeting a few Fridays ago that they were discussing these, and I think they wanted to put least squares regression either into it or make it an optional thing. I wouldn't be surprised if you might not use, I'm pretty certain you do use least squares regression, but whether you need to know the nuts and bolts of it or not, I don't think you do, but that may be something that you might want to review as well. Linear regression, and that's done by least squares. So basically, because these are all kind of involved, and we don't have lots of time left, and they're not in our course description, where everything else was, I think everything else was, I was just sort of all in favor of skipping these two sections. Actually, that Markov chain was not even in the previous book. Do you have the new book or the old? Okay, yeah. I think in the old book, the 7th edition, that section wasn't even in here. I think he ended in 2.5, but that was what our current 2.6 is. So, we just did all that. Now, there are review exercises at the end of the chapter. The odd number exercises are at calchat.com. So if you need more practice, any of the odds, this is on page 104, any of the odds 1 through 5 should be at CalcChat, 7 or 9 should be at CalcChat, 11 or 13 should be at CalcChat, 15 or 17 should be at CalcChat, 19 through 25 should be at CalcChat, 27 should be there, 29, 31, 33 or 35, 37 or 39, 41, 43 or 45, 47, and then I think beginning at 49 you get into Markov chains, and I think the rest of those are from the last two sections. So as you see, they really do a lot there. Now, I don't know, I know you're in the football, but if you're in the baseball, number 90 there, which is not one you would have anyway, but that's a Major League Baseball salaries, which probably would be a very disgusting one to look at. But anyway, that's it. Let me go. How much time do we have left? 4 minutes. That would be just about enough time for me to go run off the test. Okay? So, or do you want to, well, actually I don't have a lot of time after, so I think what I'll do is end a little early. Sorry about that.